All right, here we go. What's the derivative of sine x? Cosine x. What's the derivative of cosine x? Negative sine x. Okay, so we got to get the other ones. Now, we couldn't calculate the other ones until we finished yesterday, but now we can. So we reminded me about a couple things. We know this stuff, right? The derivative of a product. Oh, by the way, I'll have to have somebody go down and run down and get these. I printed out derivative sheets for you. So I wish I had those right now, but I don't. They're down in the office. So there's the product rule, quickly review it. There's the quotient rule, quickly review it. There you go. Low D high minus high D low over low squared. So how are we going to do the derivative? How are we going to do the derivative of tangent then, do you think?
It's sine plus cosine.
Okay, it's going to be, no, we're going to write tangent in terms of the base trig functions, sine and cosine. And so now we can deal with that because we know how to differentiate that. So how are we going to differentiate that? What rule would we have to use? Quotient rule, because I've got a quotient of functions, right? Okay, so what do I get? So, no. Low D high. Okay, so low is cosine x. What's the derivative of high? What's D high? Cosine x. Okay, minus high. What's high?
High is
Sine.
sine. D low.
What's D low? Negative sine x. Oh, okay. That's well. The first one doesn't matter on the first one, does it?
Okay,
Have I already graded that one?
I think so.
Okay, then it's not a big deal.
Okay, so
Yeah,
just reattach
yeah.
it.
Just reattach it. Yep, that works. Yep. Over the bottom squared, right? Over cosine squared x. Okay. So let's simplify that. What does the top simplify to? Cosine times cosine is cosine squared. Negative sine times negative sine is okay, what is all that equal to? 1, right? That's the Pythagorean trig identity. Sine squared x plus cosine squared x equals 1. So this is equal to 1 over cosine squared x, right? What's 1 over cosine squared x equal to? Secant squared. So we have a new rule. The derivative of tangent x is equal to secant squared x. How about that? Okay. And let's do another one. How about secant? How am I going to do secant? 1 over cosine. Okay, so we're going to write that as the derivative with respect to x of 1 over cosine x. Now, we will be able to do this after our next upcoming test. When we do the topic after that, we'll have a slightly better way of doing this one. But for now, what rule do we have to use? We have to use the quotient rule. Okay. So we're going to do the same thing. Low, what's low? Times, what's D high? 0. Minus high, which is 1, right? Times D low, what's D low? Over, I don't know why I got that color. So then we end up with, on the top, that first term just goes away and I just get sine x over cosine squared x, agreed? How could I write that in terms of a product of trig functions instead of a quotient of trig functions? I don't want to have anything in a denominator. I just want to be able to have that be a product of trig functions. What do you think?
Sine to the negative 2.
You mean cosine to the negative 2, you mean? But I don't want to have any negative exponents either. I just want to have a product of regular trig functions.
Sine x times secant.
Okay, so yeah, so I could maybe split this up a little bit. So if I wanted to write this as a product of trig functions, what would be good ratios to group together? 1 over cosine. Okay. Yeah, good. Okay, so then the derivative with respect to x of secant x is equal to secant x times sine over cosine is tangent, yeah. We got another one, okay? And I'm going to just give you the rest. We could do the same thing for the reciprocals of those two if we wanted to, right? We could have done cosecant or cotangent, and we would have ended up with very similar results. Okay, here's what we end up with. Here are the derivatives of all 6 trig functions. You already knew the base ones. Derivative of sine is positive cosine. Derivative of cosine is negative sine. Okay, do you see a pattern there? Look for patterns. Makes it easy to remember these relationships if you can see a pattern. What are some things going on? I've split it up into a blue or a black group and a red group for reasons. What are they? You notice any commonalities among the red derivatives compared to the black derivatives? The red ones are all negative, yeah. Red ones are all negative. And you notice what I'm differentiating in the right column compared to the left column? Do you see that I'm in the left column, I'm differentiating we'll just call them the regular trig functions. The right column, I'm differentiating the co-trig functions. Makes it easier to remember, right? The derivatives of the co-trig functions always give us negative results. The derivatives of the the regular trig functions, give us positive outcomes, right? And notice the other pattern. You kind of get 6 for the price of 3 here. I'm always going to be, notice that, like for example, if I take the derivative with respect to x of tangent x, that's equal to secant squared x. Well, the co-equivalent of that is the derivative of cotangent x equals negative cosecant squared. See what we did? We just swapped these regular outcomes for co-outcomes, but they're corresponding functions. Secant goes with cosecant, right? You see my point? So you could make a prediction. If we haven't memorized that one, let's say, predict what it's going to be. What's the derivative of cosecant going to be? Negative cosecant cotangent, right? Because I'm going to change these to co-trig functions and plop a negative sign in front. Everybody see that pattern? Right? If the derivative of secant x is positive secant tangent, the derivative of cosecant is going to be negative cosecant cotangent, right? If the derivative of sine is positive cosine, the derivative of cosine is going to be negative sine. That one's a little weird. The first one's a little weird. But all these other ones are very predictable, right? The derivatives of the regular tangent and secant functions give us secants and tangents. The derivatives of the cotangent and cosecant functions give us the co-equivalents of those with negative coefficients. Give me thumbs on that. Do you see what I'm getting at there? Okay. Mason, you got your thumb down. Why? I mean, like, do you see that, like, what's the co-equivalent of cotangent, or of tangent? Like, what's the co-version of tangent? Cotangent. What's the co-version of secant? Cosecant. See what I'm saying?
Okay, now it makes sense.
Okay, right. Okay. So let's just practice a couple of these. Let's practice a couple. I'll tell you what, why don't you take a second and I'm going to run down and get these things, this sheet, so I can give it to you. Take a second and just memorize those. Get out your notebooks and just write them down without looking a couple times and just memorize them. Okay, back to business. Here we go. So, okay, let's practice these. Now you've got, try to not use your cheat sheet, but tell me, oh, you can't see that. Okay, what's F prime? Right? Done. Okay, how about this one?
2x, 2x.
Okay, so you're doing, it doesn't matter the order with product rule, right? So you guys are choosing to do cotangent x times the derivative of x squared, which is, okay, plus
X squared
times, okay? So then, I mean, we could simplify that a little bit, but not much.
It's a product figure. No, I multiply together.
Okay, give me thumbs. We good? Right? Thumb up or down? What's,
Why isn't it just 2x negative cosecant?
because that's not product rule. That's not product rule, right? Product rule is this. That's product rule. The derivative of a product of functions, derivative of u times v is u v prime plus v u prime. Okay? You don't differentiate both of them at the same time. Right? I've got two functions. So Jaden, this is like my u and that's like my v. Okay? Okay, so higher order derivatives then. We've only taken first derivatives. What we've called the derivative is really the first derivative. The derivative of the first derivative is what? The second derivative. And the derivative of the second derivative is the third derivative. So in other words, what is the second derivative? The second derivative is really just the derivative. Notice how we write that. We write it as f double prime of x, 2 primes for the second derivative. That's really just the derivative with respect to x of f prime of x. Everybody see that? Yeah. Okay. And then I would do, to get the third derivative, I'm differentiating the second derivative. Now this notation is really cumbersome. Look at the notations here. Again, in calculus, we use so many different notations. I'm giving you 3 versions of the same thing for each one of these. The one that probably makes the most sense is the middle one, f prime of x, f double prime of x, f triple prime of x, and after that, we just put a number in parentheses because it's kind of tedious to write down all those primes. Same thing with y prime, y double prime, y triple prime, and then we put a number in parentheses, which means that many primes. What the heck does this mean? That's a really weird notation, but notice where the exponents are. It's d squared y divided by dx squared. What's that mean? Well, it really is intending to mean this. The derivative with respect to x of dy dx. So notationally, does it make sense why we did what we did? Why we call it d squared y? Because it looks like there's 2 d's and 1 y, and here I get the quantity dx times the quantity dx. Is that what you're doing? No, that has nothing to do with taking the derivative, but that's just the way we write this using this Leibniz notation, this ratio notation. Instead of dy dx, how are you going to say a second derivative? Well, that's how. That's how we say a third derivative. That's how we say a fourth derivative, etc. Okay? Give me thumbs. Does that make sense? Okay, they all mean the same thing. They all mean exactly the same thing. Okay, so let's practice these a little bit. Let's calculate first, second, and third derivatives. So first derivative of this polynomial, well, that's not all a polynomial. What do we get? plus done. Okay, second derivative.
Why did I get 18 plus 2.
Minus 2. Minus 2 sin x.
I was gonna say 2.
Minus 3.
Third derivative.
It's just gonna end it. Yeah.
No, we're only going to the third one.
But if it like kept going.
Yeah, so I want you to make a prediction. We're only going to do 3, but I want you to make a couple predictions about if we kept going. What's next?
18 minus 2 cosine.
Okay, if we kept going, what would happen to the first two terms?
They'd be gone.
They'd go away, right? Because notice what happened to the polynomial part of this function. The polynomials, what happens to the degree of the polynomial when we differentiate it? Drops down by 1. And eventually, when you get down to a 0th degree polynomial, a constant, you can't go any further. It just disappears. So through repetitive differentiation, polynomials get extinguished. They go away. But that doesn't happen to the other terms. They persist, right? I mean, not the constant. But the e to the x persists on a cycle of 1. It always stays exactly the same. What about the trig functions? They're going to persist. And what's going to happen to this term next time?
It's going to be the same as it was last.
It's going to be that, isn't it? Right? So trig functions persist on a cycle of 4. Okay? But they're perpetual. I mean, they stay there, but they just go in cycles of 4, right? When you differentiate. Okay? All right, now this seems pretty simple, right? No big deal. First derivative, second derivative, piece of cake, that first derivative. So first derivative is what? Okay, what's the problem with this? Second derivative is going to involve what?
Now I'm going to have to use the product.
Product rule. There you go. So second derivative means we've now got to use that dreaded product rule. Okay, so what do we get from the product rule? Secant x times secant squared x plus, product rule is plus, right? Plus tangent x times secant x tangent x. Okay, let's simplify that a little bit. What could I do? What could I do? Well, okay, yeah, but could I factor anything out? Okay. Yeah, I could factor out. You're right. So, but I could do this, right? I could take out secant x, and what's left behind? Okay, so now if we were doing something with this trig function, if we were going to do some algebra with this, say we were going to find the zeros of this or something, right? Questions on this so far?
How do you still have a secant squared x? Because there's only 3 secants.
Right, so if I factor out one of those, I'm left with a secant squared.
Yeah, but what about the secant in the secant tan x?
Okay, so this is tangent times secant times tangent. So that secant x times tangent is tangent squared. Right, so then, so that is secant x tangent squared x, right? So if I factor a secant out of each of those two terms, I'm left with secant x plus secant squared x plus tangent squared x if I divide one away from each term. Does that make sense? which is what factoring is. When I factor something out, I'm dividing it away from that term.
GCF from greatest common factor.
But do you see that? So now to get that secant out front, here, let's look at this. To get the secant out front, I'm just going to divide each of these two terms by secant x. So I could cancel that one, and I could cancel that one. And now that's out front, okay? And then, so in here, look here, there's the plus sign that connects the two terms, okay? Okay, so now imagine we're going to do something interesting with this. Like, let's say we wanted to find the horizontal tangents of this function. I wanted to find out where the derivative equaled 0. Okay, if I were going to do something like that, I could use the zero product property. I've got two factors, right? I would just want to know where is the first factor equal to 0. Or 0 would be a bad choice, because is secant x ever equal to 0? It's not, right? So say we want to know when it equaled. Right. It's going to be the loops, right? It never crosses through the x-axis. So say we want to figure out where it's 1 or something different. But it doesn't matter. Like, we're trying to set it equal to some number, like 1. Then I could subtract 1, and I could factor this whole thing out. Really, I don't even want you to worry. Like, I don't want to get this too linked to a specific example, because I don't want to get you hung up on the example. The point I'm making is, if I wanted to do something with these two factors, the first one's easy to set that equal to something and solve. The second one would be tough. How come? Like, if I wanted to set the second factor equal to 0 and solve, let's just say hypothetically, why would that be more difficult?
It's not like you're not able to find them together.
They're added. And what compounds the difficulty here? I've got two different kinds of trig functions, right? When I'm solving trig equations, I always want to try to write it in terms of a single type of trig function. And we're going to do a lot of this year, so you'll see why. But just trust me for now, that's a general tendency. You always want to limit the number of trig functions you have. So what could I do with this second factor to write it in terms of a single type of trig function? Okay, I'm going to show you a trick here. This is great. You've seen this. I'm sure you memorized these, but you forgot them. But now you're not going to forget them anymore, because I'm going to show you how you never forget them. If we do the Pythagorean trig identity, there's the Pythagorean trig identity, right? Okay. The basic Pythagorean trig identity involves sines and cosines. But what if I take each side of that equation and I divide each side by cosine squared? What am I going to get? Plus 1 equals. That's what I get if I divide by cosine squared x, right? If I divide both sides. Okay, what if I divide both sides by sine squared? Okay, so look at that. Those are my other two Pythagorean trig identities that you guys didn't have memorized probably. I still don't, I wouldn't know what those were unless in my mind I just did that. I never memorize them. I just think about taking sine squared plus cosine squared equals 1 and just dividing. That's how I always do it. So then now I could make my trades, and the useful one would be the orange one, wouldn't it? So I could, for example, I could trade this tangent squared for a secant squared minus 1, right? See what I'm saying? Okay, everybody see that? And so then now look what happens. I could combine everything, and so this becomes much easier. I get, darn it, I get Oh my gosh. How many times am I going to do that? Okay, everybody get that? Okay. And so if I were setting this equal to 0 now, it would be an easier equation to solve. I would find the zeros of secant x. I know I picked a bad choice, because but pretend there was. And I could find the zeros of this one, where 2 secant squared x minus 1 equals 0, which would just be where secant squared x equals 1/2. I could go to the unit circle and find those places. Are you getting a glimmer of what I'm talking about there? Why you want to do it in terms of a single trig function? I couldn't do anything like that if I had a mess of secants and tangents. What could I do? Right? You got to get a single species of trig function. Okay. How about that guy? Last one. Oh, we do if we hustle. Let's go. Let's go. We can do this. I thought, what'd you tell me today? You're not quitting on anything. Come on now. Okay, what do we get? Low, D, high. D high. Minus times
Yes, you have to do 3. But 3 and then it's secant.
Oh, I thought you meant that 3 one.
yeah, that one goes away, but the derivative of 3 secant would be 3 secant tangent. Okay. Over, what's on the bottom? Okay, look at the top. Does anything cancel? If I distribute the 8.
3 secant t. No.
Okay, I mean, what am I going to be? We are going to run out of time here, I think. Darn it. When are we out of here? Okay, we'll try. We'll try. So distribute the 8 secant squared, right? And this is going to give us, on the top, we're going to get 24 secant squared t plus 24 secant cubed, right? Minus okay, what am I going to be able to do there?
You can take 24 secant.
No.
I don't know what I can take out.
You could take out 24
That's a
secant.
hint.
Yeah, you
Okay, raise hands. What's the key step here in the numerator? What about the orange? What's that equal to?
1 plus secant.
Secant squared plus 1.
1 minus secant squared.
Is that it?
Where did we do?
You're on it right there.
Where is it?
The orange.
Oh yeah, right. No, where did I do my thing with the? Oh, right there. Right here. What's tangent squared equal to? Secant squared minus 1. There we go. Right? So we're going to trade this guy for secant squared t minus 1 and distribute the negative 24. And then we can cancel some stuff, right? Everybody see that? Everybody see that? Just in the numerator. The denominator's not changing. So the numerator then becomes... Everybody agree? Did I do that right? On the top? Double check me, is that right? Okay, we'll wrap that up tomorrow.
You know what time this class starts, though, Leah?
I can tell you.